Rudy, it's all yours. Thanks a lot. Welcome everyone. I would like first to thank the organizers, in particular Jaggi and Chandra, for inviting me here, and for Samuel Tam for organizing everything so expertly. And thanks to all of you for showing up. It's my first time in Hong Kong, and so far it was a very nice experience. Now, I've listened a little bit yesterday. Well, I listened, of course, intently yesterday to Alon's talk, and then I realized that my talk title was very outdated. Okay, I guess I should have done it like this. Okay, so instantly makes it much more sexy. But thanks for showing up anyway. Okay. Yeah, this is really big data, okay? And it's, to some degree it's justified, because typically when we talk about coding these days, their block lengths become larger and larger as we do more and more data, so, we can claim anything. Good, so let me get started. Now, who knows what that is? It's a diamond. Okay, so diamond stands for what?
Whatever.
Huh, for, sorry? Love. Okay, love. Okay. You're jumping ahead already. I'm getting to that. Huh?
Is it suit in a bed?
Oh, I see. Car. No. Okay, so here, what I want to get to is that diamonds, we all know, it's one of the hardest materials we can have. And so if you're like me and you get your education for movies, okay, then your science education for movies, then you know that diamonds are a symbol of something enduring, right? So as it says here in the movie title, James Bond, Diamonds Forever. And so you can imagine that I was quite unsettled and upset when I figured out that that's actually not true. Okay, diamonds are actually not forever. So carbon has quite a few what's called allotropes, so quite a few forms it can take on. Diamond is one of them. Diamond is the hardest form. But it's actually not the most stable form of carbon. So there are many other ones. Okay, so one is the graphite that you just see here, that you use in pencils. There's also graphene, which recently has come in the news, which is just a sheet of one atom thick of carbon, which has a lot of properties. There's these buckyballs. There are many other ones. But the important point is that actually a diamond here is not the most stable form. It's what's called a metastable form of carbon. And so we're talking here in regular room temperatures and regular pressures. Okay, so if you change this parameter, this changes a little bit. That's why diamonds are also around. And so this means that eventually what will happen, if you just wait long enough, okay, you will have that, okay? The diamond will go in here, okay? And so can I just ask anyone, who in here is like thinking of getting married? No, someday. Okay, no. So I mean, just a little bit of advice for free. Okay, if you're thinking of this, okay, you should really be thinking of that. Okay, but it's much cheaper, and that's a real symbol of enduring love. Okay, this will vanish. Okay, I don't know exactly what the time constants are, but nevertheless. Okay, good. But let's get back on track. Let me give you another. Way. So here it's slightly different. So what we've seen beforehand is a material that can have different forms, and there's the crystalline form, the diamond, and then there's the other form, okay, which is actually the more stable one. The crystalline form was the metastable one. Now this is slightly different. If any of you, I guess it's not something that's very topical here because it's a fairly warm country here, and depending on where people come from. But if you come from Switzerland, and if you go, let's say, skiing, where it's quite cold, then you might have seen one of these what's called heat packs. Okay, so these are simply plastic, containers that are filled with some liquid, and this is one of the sodium acetate is one of the most common one. And again, this can take on two different forms. In this case, it's slightly different. The stable form is actually a crystalline form, and the metastable form is this liquid form. And what happens is that when if it's in liquid form, okay, then it's in a metastable, so in a higher energetic state. And when you do the following, when you press, you see here there's this little thing up here. It's a metal, there are two metal discs. If you press them, then this will actually start the crystallization process. It's called nucleation. And so slowly, starting from the liquid form, it will go into the lower energy state, which is the crystal form. And while doing this, it will give off the difference of these energies, and that's exactly what will heat you. Okay, so this will warm you, and so for maybe an hour or two, this thing will give up warmth. And then the nice thing is that you can reverse this process. So if you then take the kind of crystalline form, you put it typically in hot water, boiling water, you boil it for sometimes microwave, and you again put energy in there. Then you can put it back into this higher energy state, but metastable state, and then you can recycle this a number of times. Okay, so we have now seen two. So the important thing is right now, what have we heard so far? We've heard that there are metastable states and there are stable states. Metastable state is a higher energy than the stable state. Okay, and we've heard that going from one to the other, in particular in this case here, there's something called since in here the stable state is the crystalline form, there's something called a crystallization process, so how a crystal grows. And this process sometimes has to get, in order to get it started, so this metastable state can be quite stable for a while, you might need something, okay? So you might need some local event, maybe some seed, you might need some energy locally, and this has to be large enough such that this process gets started and it goes into this other form. Okay, now what does this have to do with coding? Okay, as I will show to you is that's exactly what this spatial coupling is about. Okay, so this phenomena of what's called crystallization or nucleation process, and what I'll tell you what's called threshold saturation. This is exactly the equivalent of this. Okay, so really mathematically these are the same instances of the same physical phenomena that you see. And even though historically that's not how this thing came apart, in hindsight, is something particularly this heat pack I've learned from colleagues in physics. This is exactly what physicists have studied for quite a while. And it's a general phenomena that we can use, in particular I'll show you for coding, but you can use it in other areas too. Okay, so for example, this has been used in compressive sensing. Maybe I'll mention it a little bit. And might be used in general for graphical models. So if you do maybe something more towards machine learning or something, it might be useful. It's always useful as long as you have control of the graphical model that you have. Okay, so if the graphical model has a particular structure, has something particular that you can design, then you can use this phenomena to make graphical models behave better under low complexity iterative or message passing algorithms. Okay, so this is of course not always the case. Sometimes the graphical model is just given to you, and then this phenomena might not be applicable. But if you know that this is kind of the structure that you want, then perhaps you can design your problem to take advantage of it. Okay, so now let me get back. Okay, so we'll come back to this physics picture a little bit later. And now for the next probably 20 minutes, I need to tell you something very basic. Okay, so I'll just tell you something very basic about coding, about iterative decoding. And the point is that if you look at kind of the development over the last maybe 15 years or something, it has turned out that not much is lost if we're looking at the simplest possible case. And the simplest possible case is transmission over what's called the binary erasure channel. Okay, a channel in which either the bit, so everything is binary, input is binary, and the bit is either erased or it comes across perfectly. There are no errors in here. And so I will limit myself to this case. Everything I say, though, will be posted in such a way that it's true in general. Okay, so nothing depends really on the binary erasure channel. The results will be applicable for the general case. But the analysis and the picture and what we can draw is much simpler for the binary erasure channel. And so once we understand it there, we are pretty much in good shape, and the rest is then just a little bit more analysis. Okay, so now let me get started and just repeat a little bit, and I apologize to those that, of course, know already about coding, and introduce a little bit the language, because we need some pictures, and we need a little bit of language that we then use later on. Okay, so what do we have? We're talking about coding, and we're talking about codes on graphs. And so what we will have, we'll have a lot of pictures like this. And so what does this picture represent? It represents a binary, what's called a binary parity check code. And so what do these symbols mean? These are the bits. So in this one here, there are 20 bits here. So each of them can take a value 0, 1. And then each of those things is what's called a constraint. It's just a linear constraint over GF2. So it's just an XOR. And so, for example, if you look at the check up here, this check simply means that these bits are not completely free, but the bit 6, 7, 10, and 20 modulo modulo 2, they have to sum up to 0. Okay, so there's a linear constraint that you have on these 20 bits. And since in this case we have 10 such constraints, if we assume right now that over G of 2 these 10 constraints are linear independent, then we're starting with a system that has 20 degrees of freedom. We are taking away 10 degrees of freedom because we have 10 constraints. So this means if the code is now the set of all the solutions, all the 0, 1 bit patterns here that fulfill these constraints, and there should be at least 2 to the 10, right? 10 being 20 minus 10. And in this case, indeed, they're all linear independent, so that there will be exactly 1,024 solutions to this set of equations, and that's our code. Okay, so our code, in our case, will always be given in terms of such a graph, and there will always be bits, and typically I always plot them in red, and there will be constraints, and I plot them in blue, and that will give our codes. Okay, and I will typically talk about this as variable codes, and I will talk about this as check nodes. And so then what do we have as parameters? What will be special about this code, every linear code can be represented like this, but what will be special about our codes is that if you look at these degrees here, okay, these degrees will be very specific. For example, very often I'm going to talk about a 3-6 code, which means that every variable node participates in 3 checks. Okay, so I'm not showing this picture, this is true, but let's say every node here would have degree 3, and here every check checks exactly 6 of these constraints here. Okay, so this would be if I'm talking about 3-6 code. And so now, I always draw these small figures, but what you really have to think about is very large. Okay, a code like this would not be length 20. A code in practice would be at least a length 1,000, but it would be much more likely even much larger. And for example, if you look at things like optical, code lengths of, let's say, 60,000, 100,000 would be nothing special. And you could even implement things like, let's say, 1,000,000 if you can just put it on a chip. Okay, so they can be fairly large, and so you should really think of this as a fairly large thing here. Although we always draw this as something small, but you should think of the degrees as fixed. Okay, so the degree is always 3, no matter what the length is. The degree here might be always 6, no matter what the length is. And then we're simply gonna, think of very large codes, and we're gonna try to figure out how these things work. Now, the rate already told you, right? So I told you that the set of code words is the number of bit patterns, that fulfill these constraints. Okay. Okay. Yeah, I'm not sure what to do about that. Yeah, that's true. And I see there were some references down there. So Sid, maybe you can check. Okay, I'll just continue right now, and then we'll see. Maybe you can fix it next. Okay, because there were actually some references down there which you couldn't see. Okay, so just the rate again is simply the number of degrees of freedom that are left divided by the total number of degrees of freedom. So in this case, 20 minus 10 over 20, which would be a rate and a half code. Okay, so yeah, you see again. Okay, so now all I told you so far is that I pick certain degrees, okay, but I haven't really told you how I pick these connections. And there are many ways of doing it. And let's just pick now some kind of the simplest version. The simplest version is the following. You simply first decide what the degrees of the various modes are. So in this case, for example, they're all degree 3, and here they're all degree 6. And then what you're doing is you have, of course, in order to have a bipartite graph here, you need the same number of, what we call them, sockets here. Okay, so you have 12 sockets here, 12 sockets here. And then what you do is you simply pick a random permutation, and you pick it uniformly at random, and then you match it up. So let me just show you this. So this would be one thing, and if you pick a different random permutation, you simply get a different connection pattern.
So here on the internet, it's looking fine. What's happening is we seem to have a choice of either having it slightly fuzzy at a lower resolution, or
so maybe let's try to do slightly fuzzy at a lower resolution and see what happens.
Okay. So, wait, I thought we were ready.
I think it was the 14.
14?
It's 16.
All right. Out of range. It's coming back. Oh, it can't do any more than this. Oh, okay, maybe.
Okay, I think this might not be here, so let's check this here. Okay, let's check. I think this might be fine. Thanks a lot.
If it doesn't complain, it seems to complain. Where's your PowerPoint? Oh, Keynote?
It's this one. Reopen just.
Yeah. I didn't confirm the change. Okay.
You think it's okay now?
Okay.
Okay, let's try. Okay, so you can see that this is the connection. So this is typically the model we take. The other model is possible too, but this is how we create the code. So we typically talk not about this specific code, but we talk about an ensemble. Okay, we talk about a random choice of these connections, and then we typically analyze how this behaves in average, and then we would prove what's called concentration theorems that tell you that most instances would behave the same. Okay, so now there's another way to represent this, and this picture, will also be quite useful. This is something that goes back to Torp, who was a student of McLean's at Caltech, and that's what's called a protograph. So this picture here represents exactly the same as the 3.6 code that I showed you beforehand. So what it is, it's just basically a sample. It just shows the types of the nodes. So this would be a check node, and it has degree 6. You can see 6 of things going out, and these would be 2 variable nodes. And then, as you can see, both have degree 3. And so how would that represent a whole code? It would represent a whole code because you would replicate it. Okay, so this is what's called a graph cover. You would simply take many instances of the same one. So this would be a cover with just m is 5. But again, think of maybe 1,000. And then how do you now make a code out of this? You make a code out of this by taking like edges. So for example, these edges that are here, let me call it an edge bundle. All these are the same kind of edge. And now simply taking permutations of these. Okay, so you take these edges, and now you insert them again, but just reconnecting different values. Okay, so one way you can think of them is just think of them as really covers. Think of them as sheets of paper, and then you're simply connecting from the edge bundles. Edges likewise take a random permutation and connect different sheets on different levels. Okay, and you do this with all of them, and then again you get the same for all the other edge bundles. This is, strictly speaking, not exactly the same ensemble, but it behaves asymptotically in exactly the same way. Okay, so sometimes I will simply draw these kind of photographs, and that's when I draw a photograph, it's understood that this is just kind of a sample for it. It's just like a model for the graph, and then you really take many instances of it, connect them together, and that's how you really construct your code. Okay, so now we know how to construct code. So now the next question is, well, how do we do the decoding? Okay, so there's typically 2 different ways how we can decode. Either our criterion might be that we want to optimize maybe the bit, or we might want to optimize the block error probability. It's slightly easier to think about optimizing the bit error probability. So what is it that we would like to do if we could actually do it? Okay, so we would like to minimize the bit error probability. And so the way we would do it is that if we're looking at the ith bit, so we have a code, we take a code word from this, we transmit it over the channel erases, let's say, some bits, and now we want to figure out the value of this particular bit. And so the problem that we would have to solve is, what we would have to do is we would have to take the argmax of this posterior probability. So given the data that we have, what is the most likely value here of the bit xi? So we want to find the argument that maximizes this posterior probability. And now, there's 2 tricks that standard are played in here, okay, which are, of course, standard if you've ever seen a communications chain. The first thing is that what we're doing is, rather than looking at bit xi here, so let's expand it. Let's put here the whole vector x, okay? and writing the whole vector x and then summing it out. So I'm going to write p of xi given y as p of x, where x is the whole vector given y. But then I'm summing out over all the other variables xj's, okay, except for the xi. And then the second trick is that I'm going to use the base rule. So I'm going to turn things around. So rather than writing p of x given y, I'm going to write p of y given x, and then I still have the p of x there. Okay. And so why do we do this? Because now we have all the quantities that we have a handle on. So what do we finally left with? Well, this is the summation that comes from this law of total probability when we took the whole vector in and summed out. And then these are the two parts that are still left from the base rule. So this one represents p of x, and I'll talk to it in a second. And this is the p of y given x. But since this is a memorized channel, this is simply the product. P of y given x is simply the p of yj given xj. Okay, so this is a nice product form. Now here what should really be is p of x. What is p of x? Well, p of x is just the probability of having a certain word x. Since I know the code, this p of x is a very simple form. Either it is a code word, okay, in which case I assume a uniform probability of all code words. So the probability is 1 over the size of the code. Or it's not a code word, then for sure it cannot be the transmitted word, right? Then it's 0. Now, since scalars do not matter in this case, what I can simply do is I can, rather than writing here p of x, I just write an indicator random variable, an indicator function, which simply means this is 1 if it's a code word and it's 0 otherwise. Okay, so this is equivalent to this probability p of x. It just differs from it by a fixed scaling. And so what I have to do is now I have to find the argmax of the xi over this thing. Okay, so that's the standard formulation that I have to do it. I wanted to do optimum decoding. And since this is the only slide which depends now a little bit on the BEC, but will not later use it. So what would I have to really do for the BEC if I wanted to do this? Well, I know that the code, okay, so I know that the code so fulfills the following constraint. This matrix here is a 0, 1 matrix, which is just the adjacency matrix of this bipartite graph that I showed you before. Okay, this just encodes the connections that I had beforehand. And so the vector x, so this is the vector x here. So this vector x is such that it fulfills all the constraints. So for example, the first row might correspond exactly to this first check node that I told you beforehand. Okay, so this has ones at exactly those places which xi's I'm picking. Okay, and so this has to be 0 because we set this parity check. So the code is the set of all the set of 0, 1 vectors that fulfills these constraints with this parity check matrix just given by this bipartite graph, the adjacency matrix of the bipartite graph that I've shown you before. And so this is what we know. Okay, now we get a certain received vector now. And the received vector will have two things. Some of them will be known and some not. Okay, so the erased ones, these are the erased ones, let's say. And I guess I color-coded them as white. Okay. And the kind of darker ones are the ones that I actually received. Okay, so this is my vector. Some of the values I know, and some of the values I do not know. Okay, and so now I need to find out. I want to see if I can complete this vector by using these constraints here. Right? So what would I have to do? Well, those that I know, I can simply take the corresponding columns out and separate it. Okay, so I separate it out in the known part and the unknown part. The known part I can just multiply it out with some known vector that I have. Okay. And so now this is an unknown vector, okay, and that has to fulfill these constraints here, okay. So I'm trying to figure out if there's a vector that fulfills has this particular right-hand side, and so these are simply the set of equations here, okay. Now, in principle, this of course you can do via linear algebra. So for the BC, this wouldn't be a problem, and it would only be, you can do it in at most n to the third operations. Potentially, you can do it better because it's a sparse graph, but you can certainly do it. Unfortunately, this only works for the BEC. Okay? So only for the BEC you have this kind of linear algebra interpretation. And if you wanted to do this for the Gaussian channel or some other channels, this wouldn't work. Okay, so that's why we are not going down this path by trying to solve a linear equations, but we're trying to look for an algorithm that works in general. And you actually all know this kind of algorithm. Okay, so so this is now, and let me just go directly to the algorithm. So you kind of all know this algorithm. It's a message passing algorithm. You know it even if you have never actually explicitly looked at it, because I hope, okay, in your younger years, okay, you did exactly that, okay? Let me message passing, okay? So typically it's in high school, okay, and you pass messages back and forth, okay? And you hope that the teacher doesn't find out, okay? So here we don't have a teacher, but the message or the purpose of the message is exactly the same, okay? You're trying to send information from one point to another one via some other intermediate points. So let me try to explain exactly how this works for the BEC, okay? So how do we do message passing for the BEC? It's an extremely simple algorithm. Now the way I'll explain it will be exactly how it works for the BC, but the basic principle will also work for the general case. Okay, in the general case, we will deal with slightly more complicated messages, which are probabilities, but I will not get into it. The basic principle is the same, and the type of an analysis also exactly the same. So how does it work? So it's something, an extremely simple example. So we have this code here. So this code has 3 bits and 2 checks. Okay, and they're linear independent. So there are actually just 2 code words in this code because there's 1 degree of freedom that's left. Okay, and so now we sent one of these code words, but unfortunately 2 of the bits have been erased. Okay, so what we have left is we have 0, question mark, and now we hope that we can actually recover. Okay, so how will we try to recover this? Well, we do it as follows. The message passing starts by sending the known information from the left side to the right side. Okay, so we take whatever, we copy whatever we received, we copy it on the edges, and we send it to the right. And now we hope that we can make local greedy deductions about some of the unknown bits from the known ones. Okay, so how do we hope to do this? Well, let's look, for example, on the bottom part here. Okay, so let's assume we would try to figure out what the value here is. Right, so how could we hope to find the value here? Well, we get messages, so remember, the mod 2 sum of this has to be 0. If we know actually this value and we know this value, right, and then we would know that the sum of all 3 values is equal to 0, then we could figure out what this value here would be, right? Okay. Now, unfortunately, it turns out that this value is 0. That's good, but this value is question mark, so we can make no deduction about this value here. Okay, so the message passing rule is that you get in, so you're trying to send along every edge a local deduction about what this bit should be. But unfortunately here you see a 0 and you see a question mark. You cannot deduce anything. It's a question mark. Okay, there's nothing you can deduce. Okay, but what about some other ones? Well, let's look maybe on the top. Okay, so let's assume we wanted to deduce what this value was. Okay, we know again that the sum of the 2 must be 0. But from the standpoint of this one, if he tries to deduce this, he knows that since the sum of the 2 is 0 and he knows this one, he knows that this one must also be 0, right? And hence he will send now along this edge, he deduces that it must be 0, that he will put on this edge. Now you do this for all the edges. Unfortunately, it's impossible to see what these things are. I apologize, okay? Unfortunately, it's hard to see what these values are. And you transmit them over to the left side. Okay, there should be a 0 here. And since you now know this value here, you have actually decoded this value here. And now you start the whole thing again. Okay, so now you know more on the left. You again send the information you know on the left again to the right. You try to again make greedy deduction. You send it to the left, and you go back and forth. Okay, and so that's the message passing algorithm. Okay, the key ingredients are that you do computations only locally. Okay, so for everything you just locally greedily try to figure out what's happening. And there will be one distinct message sent along every edge. Okay, so messages going out from one check node along different edges can be different. Okay, it's just the local deductions about what the other bits tell you about one particular bit that you sent the message to. Okay, so that's the algorithm we will always talk about, and we'll say sometimes it's BP algorithm or just message passing algorithm. Okay, but the general term is belief propagation, because in general what you send here are probabilities, and not like in this case, simple case where you're just sending zeros or question marks or ones. Okay, so that's the algorithm we do. And so now the question is, how does such an algorithm perform? Okay, so let's take again our favorite example. We take a graph like a 3-6 graph. Okay, and now what we think about is we'll think about larger and larger instances of this graph. Okay, so the important thing is that, again, every node here will have degree 3. Every node here will have degree 6. The connections here will be random, okay, so as I showed you beforehand. And now we try for a very large instance to see if we can figure out what the performance of such a combination is. Okay, so let's do the following experiment. On the bottom here, we plot the channel parameter. So this would be if the channel was perfect, no erasures. This is if the channel is bad, okay, all erased. And on the axis here, what we will plot is, what we do is the following. I pick randomly a code. I pick randomly a code word. I send this code word over the channel. The channel will do its deletions or erasures, okay, according to every bit erased independently. Then we run this decoder here, okay. And so if you think about this decoder here, you will see that this decoder, what happens is that at any instance of time, either this decoder will be able to make new deductions, or if at some point in some iteration it doesn't make any new deductions, it will simply be stuck forever. Okay, so it has a well-defined point to which it gets. You simply run it until it can no longer make any greedy deductions. At that point, you will count how many bits are still erased, and you will simply plot this here. Okay, so that's what we will plot. So let's do this experiment. We'll do this for some particular value epsilon here. Okay, and so if the epsilon is very large, then there's really nothing much we can deduce. Okay, and we'll be stuck somewhere at a value, large value. And if we now do the same experiment for some smaller epsilon, it's kind of intuitive that if the channel is better, right, that we'll be able to decode more and more, right? So these values should go down. Okay, so that's not very surprising. What's perhaps a little bit more surprising is not that they go down, but that at some point we have a jump. Okay, so the jump will be, there will be some point here, and we'll learn in a second what this point is where, from some smaller and smaller value, this actually jumps to 0. Okay, so what we're interested in is exactly this transition here, which is called the phase transition, where the behavior of this decoder or this combination changes fundamentally. Okay, so we'll try exactly to understand where this happens, why this happens, and how good this is. Okay, so of course, what we would like to do is, what does this mean that we down here? It means that we can decode for very large codes reliably, and of course, we would like to make this point as much to the right as possible. Okay. Maybe just checking to make sure that we are all still awake. If we have a 3/6 code, right? 3/6 code, as we said before, it has rate a half, so that's a rate a half code, and that's an erasure channel. How good can we hope to do this? Okay, what is the maximum value of epsilon for which we could possibly hope that any code and any decoder might work? Right? It's the capacity for, if we do this, the capacity for the erasure channel is 1 minus epsilon. That's the R. We have given the R, which is a half. Okay, so this means that the Shannon epsilon, the maximum epsilon, can possibly hope that it will work for, will be a half. Okay, so in this case, it's about 43%. So that's not so bad. Okay, but it's not quite a half. Okay, good. Now, so let's now see if we can figure this out. Okay, so what we're trying to figure out is now in the asymptotic case how this decoder might work. Okay, so what do I mean with this? I mean that, remember, we had this message passing rules, right? And so we have two sides. So let me first check maybe with the check note side. There's the check note side here. So we have incoming messages, and we have the variable note side here. Variable, and this is the check. And to stick with our notation, let's assume that the degree of this node here is dl, and this degree is, let's say, dr. Okay. So that's the total degree here. So now what happens is that these messages coming in can either be erased or they can be known. Okay. And what I'm trying to figure out, what's the probability that the outgoing message is either erased or known? So the variable node, I have this, and I have an observation here. And this observation is erased with probability epsilon. Okay? So now let's assume that the probability that each of these incoming messages is erased is y. Okay? So y is the probability that incoming message is erased. And let's assume that all these erasures happen independently. Right? Now, when will the outgoing message be erased? When do I not know what the value of this particular bit is? Right? I don't know it if this is erased and all the incoming things are erased. Okay, if any of them is known, if any of them tells me that it's known the value, then this value is known. Okay? So what is the probability that this thing is still erased? But all of them have to be erased. So I have to have an epsilon, and I have to have a y to the dl minus 1. Okay, so the probability that the outgoing message in this case is erased is this. Is that clear? Okay. So it's simply because if a single message is known, right? They have to be consistent, so two messages cannot tell you something differently. There are no errors in this case. But then the only way is that as soon as a single message, either this is not erased itself or any of these messages tell me what it is, then it's actually not. Okay, so it's epsilon to the y to the dl minus 1 power, and there's dl minus 1 because I have only the incoming messages that I'm counting here. I'm not using the incoming message along this edge here. Okay, so that's a very important principle for the message passing principle, that I'm only using the information coming somehow from the other part of the graph. Now, what about here? So let's assume now this is x. Let's assume the probability of A share is x here. Okay. Now this is an XOR, right? So the value outgoing here is the XOR of the values coming in here. So when can I determine the value of this XOR? The only way I can determine it is with all the values here, right? If a single value is not known, if I have, let's say, 1 and I XOR a random bit to it, okay, and the bit is, let's say, equally likely to be 0 or 1, then I can't say anything about the outgoing value, right? So I can only say if all the values are known. So it means the probability here that this is erased is 1 minus x to the dr minus 1. Why is that? 1 minus x is the probability that one of them is known. 1 minus x to the dr minus 1 is the probability that they're all known. Okay, in this case I can know it. And 1 minus this is the probability that it's known. Okay, so these are the message passing rules. And so this is exactly what is written here. So let's go back. So that's exactly what we have. Okay, so just repeating again these equations here, and we see how things proceed. So this is exactly the equations that I put. Okay, so this is at one step. And so now what happens? So imagine now that you have a very, very large graph. Okay, and now imagine the following. Where do my messages come from, right? So I'm taking a particular node, and maybe I do 3 iterations, and I'm asking, what is the message at the third iteration that arrives here? Well, I can basically go backwards and see where the messages arrive. Well, my messages arrive from my neighbors. Those, again, get their values from neighbors of their neighbors, and this goes down. Okay, so this whole thing is when I'm looking out here, and I'm tracing where the message comes from, and I do, let's say, L iterations, what I will get here is a computation graph that tells me exactly where these messages come from. Okay? Now the point is that if you think of the following limit, first think that you have a fixed number of iterations, and then you make the block length go to infinity, then with probability going to 1, this computation graph is actually a tree. Okay, so that's maybe something, one of the exercises that we can do to figure this out. If you simply think of the previous probabilistic model, what's the chance that maybe this one is exactly the same as this one? Okay, this probability goes to 0. Okay, so that's a very specific limit, and I come back to it. The limit in which you have a fixed number of iterations, and then you look at the block length going to infinity, and you look what this tree looks like. So this, why is that nice? Because if we have this, then it means that all these observations we have here, along all the variables here, they're all independent, okay? None of these things that we see in the computations repeat, and this model that we have here, that we assume that they're all independent, is indeed correct. So what does this mean? Let's look at this. So this goes back to, the whole idea of course, low density pair check goes back to Gallagher, and the analysis for the erasure channel in slightly different terms, not really using this language, but using something slightly different, goes back to Louis, Mitzenmacher, Spielmann, and Stemann, and Chocolahi. Unfortunately, I apologize that you can't really see this here. And so how does this go? Well, we're just repeating now this recursion that we've written down here. So we start on the bottom, and our erasure probability is epsilon, because that's just what the channel tells us. And now we simply do one recursion after a time, right? So at the first time, this goes into check nodes, and we have to use this check node recursion, right? So this epsilon gets converted, and the epsilon gets converted to 1 minus epsilon to the dr minus 1 power, okay? But instead of epsilon, I write here x of 0 at iteration 0. And so this will give me now the probability that these messages are erased, right? Now this goes, again, into this one here, and if I'm checking what's the probability that this is erased, well, now I have to use this recursion here, and so this is the other recursion here, and I plug this in, right? And so I can go simply up, down the tree, and so I can figure out at the alpha iteration what will be, under this model, the probability erasure in this graph, okay? Now, what do we want? We want that this probability of erasure goes down to 0, right? So the question is, in this recursion, will this recursion, starting with epsilon, will this go to 0 or not? Okay, and in particular, for what values of epsilon will it go to 0, right? We want this value to be as large as possible. Okay, so, okay, unfortunately, it's also not so easy to see. So what is the important thing? If you put these two recursions together in one, you will see that if you have a particular parameter epsilon, and you have an erasure probability x that comes in, after exactly once bouncing back and forth, the erasure probability will have transformed to this one. So f of epsilon x is this function epsilon of 1 minus x to the dr minus 1 dl minus 1. So the x will be transformed in this, right? And the hope is, of course, that this x, after one iteration, is smaller, and then you do another one, will be smaller, 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 and that this x will eventually converge to 0, right? That's the hope that we can actually do. So now, it's not very hard to see that this function here is increasing in both its arguments. So it's increasing in epsilon, which is obvious because this is non-negative, and this one is simply a constant here times this non-negative thing here. In x, it's also not very hard to see that it's increasing. And because it's increasing in both, what you will see is that the following, that if you're looking at the L plus 1 iteration and you look at the value, if you just plug this in, that it's increasing, you will see that this thing here will be smaller equal than what you have in L, in the alpha iteration. Okay, so this means that the estimate will improve. So what you have is you have a scalar recursion, which is monotonically decreasing and is bounded below by 0, right? Because the erasure probability is something that's non-negative. So this must mean that this recursion must converge to something, okay? Now what we hope that it converges to 0, but we don't know that yet that it converges to 0, but it must converge to something. So we simply start this, what's called this dense evolution recursion. We plug them in, we do more and more iterations, it will converge to a number. And we're hoping to see that this number converges to 0 for very large values of epsilon. Okay, so now let's just do this. So let's run this. So for exactly this case, what I do is, this is again the epsilon, and here I'm plotting again this erasure thing after a certain number of steps. I'm simply looking where it converges to and see what it happens. Okay, so if we do this, after one iteration, if I start with a certain epsilon, after one iteration, that's what I get. Okay, after one iteration, the recursion gives me this. If I do 2 iteration, it goes down, goes down, goes down. Okay, and you can see, now it's not surprising that for very small epsilon values, it very quickly goes to essentially to 0. For very large one, it basically stays, nothing happens. Okay, but again, you can see that this curve becomes steeper and steeper. And there's exactly this transition here, which happens, we call it the BP threshold, and this happens around 43%. Okay, so this is very similar to the picture that we had before. Now, this is exactly equivalent to the experiment that we ran before, and except that now we have equations that predict exactly where this thing will happen. Okay, so now just one more extra thing. That's a small detail. Okay, so far, I have cheated slightly when I plotted it, but fortunately nobody caught me. So what I plotted actually was not exactly what I said. Okay, it was not exactly that I'm looking at the probability of error at the end. What I plotted is some slightly different value. It's something which is called the exit value. Okay, so x is simply the probability of ratios that I have in there, but the exit value is something slightly different. And what is this exit value? So the only difference is that the final recursion, instead of using this one here, you're using this one here. So what is the difference here? You can see that there's no epsilon in here, right? There's an epsilon, there's an epsilon. But on the other hand, you have degree dl, versus here you have degree L minus 1. So what is the interpretation of this estimate here? The interpretation of this estimate is the following. You do exactly the experiment I did beforehand. And now for every bit you do the following experiment, you forget about, at the end after you have done the decoder, you forget about whether the bit itself has been received or not. Okay, you ignore the value if you actually see it. And you check whether or not the other bits were capable of telling you the value via the messages. Okay, so now you have actually DL messages, all of them, you ask whether or not they know the value. And if at least one of them knows the value, that's what you know. Okay, but you ignore the observation itself. Now, it's clear, right? Epsilon is just a constant, and between the two, you can go back and forth. So it's clear that once you don't give me one value, I can give you the other value. Okay, so there's a priori, there's no difference right now, but we'll see a little bit later that it will be crucial for all the observations that we have that we're using this quantity. So this looks exactly the same as beforehand, except that now, I have this one. So now initially, if I know nothing, since I don't take the epsilon into account, the initial estimate is 1. Okay, I know nothing because I can't take the observation into account. I do exactly the same kind of things as beforehand. And these curves are in one-to-one correspondence, so I could have plotted any. It's just that the shape looks a little bit different. Okay, so this is kind of the shape. And so now if we go back to our experiment, this is actually, exactly what I had plotted to you originally. Okay, so what I plotted to you was actually the exit value. And so if I do the experiment, and now I plot these fixed points that I get, you can do the experiment, you will see that you have a perfect degree. Okay, so we now know, in principle, how to analyze for the BC, but there's still a slightly nicer way of doing it. Right now, what we would have to do is we would have to do the following, right? For every epsilon, I need to start the recursion, I get a fixed point, that fixed point gives me one of these points here and then plot it, okay? But I claim that there's actually an even much easier way of doing it. So maybe first a remark before we get there. Maybe you get slightly suspicious at that point, right? And you should, because what did we do, right? We had this sneaky limit in there, and the limit had to do with the fact that I told you that these are all independent, and that had to do with the fact that I'm doing a fixed number of iterations first, then I let the block length go to infinity, and then later on I take an infinite number of iterations, right? So there's a certain limit in which I took this, and that limit made it very easy for us to compute. But of course, in practice, you don't do this, right? What do you do in practice? You have a fixed block length, and basically you run an infinite number of iterations. So this basically corresponds to the reversal of the two limits. Block length going to infinity and L going to infinity. For the BC, it's actually very easy to show that these two give you exactly the same result. So it doesn't matter in which limit you take it. You can take the limit in any case. So whatever I showed you is the true result. It's robust against whatever model assumptions you take. Okay, so there's nothing really that we did that is sneaky. It's just a little bit. The other one is that, which I haven't shown to you, is there's typically some concentration results that tell you that right now we'll analyze the average of the performance. If you look at finite length codes, you also have to look at what's the probability that a specific code you pick is good, and that you also can do, but we will not talk about it. Okay? Good. So now let's go back to this. So what did I tell you before? And so we had these recursions, right? And so these were the recursions that I had. I start with epsilon. After one step, I get this. After full iteration, it goes like this. And so at the end, right, I converge to something. And since these equations are actually continuous functions of x, it's not difficult to see that the final point that I have to converge to must be a fixed point of this equation, of this dense evolution equation, right? So we know that this sequence is decreasing. It converges to a point. And since the recursion is continuous in the parameter, this point itself must be a fixed point of this recursion. Must be a solution to this fixed point recursion, right? So this means this fixed point that we computed, I could also compute it not in a dynamic way, but just statically, but just looking what the fixed points of this equation are and plot them, right? And indeed, beforehand, that these are exactly the fixed points here. But it turns out that there's an even easier way to do it. Now, here it's a little bit difficult, right? What do we have to do? I pick an epsilon, and then I have to find an x such that this is the solution to this fixed point. That there's no trivial closed form solution for this in general. Okay, it's some root of a polynomial. I mean, you can do it, of course, in an efficient way because it's just the root of a polynomial, but there's no explicit way to write it down. But there's a much easier way to do it, right? What is if we don't solve x as a function of epsilon, but what is if we solve epsilon as a function of x, right? And so if we simply solve this equation for epsilon, right, so we have this equation and solve it for epsilon, then we see that no matter what the x value is, there's always an epsilon that makes that to a fixed point, right? And that's not trivial to write down, right? So the epsilon as a function of x is trivial. And so now I can actually plot this curve. So this is again the curve of fixed points here. So now if I go over all x, I simply have this curve. It's a parametric curve, right? So I have, on this value, I have here the x value. On this axis, I have the epsilon, and they're simply parametrically as a function of epsilon, a function of x going from 0 to 1. I plot this curve. Now, there's a small difference between them, right? As you can see, the top part is exactly the same as this part here, right? But there's also the bottom part. So these are fixed points here that you never see in the top picture here, right? So what are the top fixed points? The top fixed points are the ones that you can get to. These are the ones you start with an unknown channel, with an, with just a channel epsilon. You go, and you go down, and eventually you will hit one point here. But there are other fixed points on the bottom here, which are unstable fixed points. So fixed points that, no matter where you start, you will never end up there. But we will see that they play, as an important role for our analysis as estimates. Okay, so now let's summarize. What do we have? We have, transmission over the BC. We have a very simple ensemble right now, 3/6 ensemble most of the time, or in general, a DLDR ensemble. We know how to plot the set of all fixed points, right? And so once we do this, what is our threshold that we have? We simply look at the point that's the first to the left, the furthest to the left. We look down here, okay? So we're maximizing this epsilon as a function of x, and that's, we're minimizing the epsilon as a function of x, and that's exactly our BP threshold here. Okay, so we simply look at what's the most left this curve ends up, and that's exactly our threshold. Okay, so that's fairly easy to do, right? So if I gave you now not the 3/6 but the 4/8 code, you simply plot this here, you get a curve that looks somehow similar. You plug this in, you look at the leftmost point. That's the fraction of erasures you can decode with. End of the story. Okay. Any questions so far? That's all I'm going to say about the standard analysis of the uncoupled case, and I'm going to go to the coupled case. Yes.
You optimize over RDR and the
Okay. Right. So, much of thanks for asking. Okay. So much of coding in the last, since LDBC codes were rediscovered in around, were first turbo codes in '93, and then later LDBC codes were rediscovered. There were quite a few people, McKay and the people I mentioned beforehand, that somehow independently were part of 3 groups that more or less independently rediscovered this version of iterative codes and LDBC codes. Much at that point was then trying to find good codes, right? And so what does it mean to find good codes? It means that you want to get this BP threshold, so the leftmost part of this curve here, as much to the right as possible, and in particular close to the Shannon threshold, right? So we said that for 3/6 code, that is about 43%. What we really would like to have is 50%, right? And so in this work that I mentioned before, by Luby, Mitzenmacher, Spielmann, Stemann, and Chocolai, they found a way to construct codes which indeed have this property, so that their BP threshold for the BEC is arbitrarily close to the Shannon threshold. And how did they do it? They had a small variation on the problem, and the small variation is that instead of picking just a single left degree and a single right degree, you allow degree distribution. So you allow some fraction, let's say 20% of the nodes are degree 3, 40%, let's say, are degree 7, and whatever. Okay, so you allow some fractions. You allow some fractions on the left, some fraction on the right, and now you can do exactly what David had suggested. You can try to optimize. Okay, so the degree distribution will determine 2 things. Number 1, this curve, the shape of this curve. Now the analysis is almost exactly the same, except that now having a fixed degree, you will have a polynomial here, but otherwise this looks formally exactly the same. So it will give you, for a fixed degree distribution, give you the threshold, but also the degree distribution encodes the rate. Okay, so the rate you can see in the degree distribution. And so what you now want to find is a degree distribution that gives you a fixed rate, whatever you want, and maximizes the threshold. And they could explicitly solve this in some, very beautiful way. They would do that. And so for the BEC, it was known, I think this was about in '98, how to actually achieve capacity achieving, so for the BEC, capacity achieving codes that follow exactly the principle described to you. Okay. Now, the problem is that if you do this for slightly more general code, so you do this for general channels, you do this not for the BEC, but you do this for Gaussian, then even though this dense evolution and everything I told you has an analog, now we are no longer dealing with scalars, no longer with numbers, but we're dealing with probability distribution. So each of these fixed point now is really a probability distribution. And then it becomes much more difficult to analytically handle that. Okay. Now, why don't we worry about that, and why don't I tell you about the irregular ones? Because the extra structure I will tell you about now will make it possible to achieve capacity without doing any optimization. Okay, and so for us, regular is sufficient.
Actually, my question is,
Sorry, long, irrelevant answer to a short question.
yeah, pretty much.
Thank you.
Because what I was trying to say is that you earlier mentioned 3, 6.
Right.
But we could do 4, 8.
Right.
Or we could do 5,
So
10.
everything I wrote down here is, yeah, is this. I'll get back
So
to.
what I meant is.
I'll get back to exactly. You will see some slides where I'm getting back exactly for the regular case, but we still stick with the regular case. But we'll see what happens if I'm taking something different than 3, 6. Okay. Thanks.
I didn't really get how each iteration.
Why the iterations were independent? So the point is the following. So if you look at the So remember we had this model, and you should think of the code with maybe maybe 1,000, maybe 10,000 nodes here. Okay, I'm just drawing something very small here, right? Now let's assume you're doing whatever 2 iterations, right? And you want to know after 2 iterations what it is, right? Now what will happen? You look at the second iteration. Let's assume this thing here is connected to these 2 guys here, right? So it means there will be messages flowing from here to here. Right? Now, in turn, where do these messages? How they are computed? Well, these nodes have some extra neighbors, maybe these 2, right? So it means the message that will flow here in the second iteration comes in the 1.5 iteration from here, right? So the message will come from here. This gets processed, and then the message will flow further, right? That's the rule. In turn, these things will again be, come from somewhere, right? So if you chase this down where this thing comes from, generically, you will get a tree, right? You get a tree of, and each of these things has labels, right? So this is maybe node 1, this is maybe node whatever, A and B, this is maybe 2, 3, 5, and 7, etc. Okay? Now, when will these messages all be independent? They will be independent if, for sure, if none of these things repeat. If none of these things repeat, then all the erasures that you're seeing, the erasure channel, flips or erases every bit independently, then if they have no repetitions in here, right, then all the erasures are independent, okay, and then all the messages will be independent. So my assertion is that if you take a fixed type computation graph here, okay, and you think about a fixed number of iterations, but you let the size of the tree of the code go to infinity, and you look at how the model of the graph comes about, right? So where was this connected? It was connected randomly to, let's say, 2 of its neighbors. Okay, it goes somewhere. Now, okay, what's the chance that, for example, these 2 edges already go to the same guy, right? Well, the chance is if there are, let's say, n nodes in here, right, then the chance is proportional to 1/n that these 2 edges will be going to the same guy here, right? If they go to the same guy here, you're out the way, right? Yeah? So in the first iteration already, the chance that these 2 are different is something like a order 1/n, okay? Now, you do the same thing, you chase it back, and you will see that there's a finite number of chances that you have to get overlap, right? And each of them, the probability will be of order 1/n that something bad happens to you, right? And there's a fixed number of edges that you have in here. So the probability that something bad happens, that this is not a tree, is of order the number of edges divided by n. So if the number of edges is fixed because you do a fixed number of iterations, but you let n go to infinity, that probability goes. Okay, so with probability going to 1, this computation graph here will be a computation tree, and if it's a tree, then this message is saying.
What is that computation? What does that look like?
If it's not a tree, so it could be simply, in the simplest case, that these 2 things, for example, connect to the same thing. Okay, you could have double edges, right? Or you could have, for example, maybe a cycle of length 4. Make sense? Yes.
Sorry, I'm finished. So if you push this dr and dl to larger noise by fixing the ratio that we want to have, it's pretty clear that you could get the capacity. Right?
No, I'll get to it. Okay. we would have been out of.
No, yes, the answer is no.
Yes, it's no. Right? Okay, I'll show you in a second. We'll get to it. Okay. So actually, in this case, 3.6 is the best you can do at this stage. Okay. But well, it's a good question. We get exactly to this point. Okay. Now, so now we get to coupled codes. Okay. So this is all I'm going to talk about the uncoupled codes. And maybe if some things were a little bit fuzzy, I hope that at least somehow the pictures, basic idea of the pictures made sense. That the basic picture will show you is exactly the one with this curve that I have here. This one curve, and we'll call it the exit curve. And the leftmost point was the one that determined the threshold underneath. So now we get to the coupled case, right? So what does the coupled case mean? And then we'll connect it back to the physics. Okay, so this is exactly something like what we had before, right? So this is like a code that they had, and again, you should think of this as maybe length 1,000, but I draw it of some much smaller length because I will need to draw some pictures and on this small screen. So what we do now in the coupled case is the following. I don't pick one, but I pick actually several of those. And for no other reason than that it gives you a nice picture, what I'll do is I'll line them up in such a way that they lie in a circle. Okay? So what I have now is maybe whatever, 15 of those. And they are independent copies, okay? And each of them has the same structure. Each of them is, let's say, something like a 3.6 code, okay? On here, it's not shown like a 3.6 code, but think of each of them and say maybe degree 3, each of them degree 6 here, and maybe you have 15 of these copies. Well, if you did it like this, okay, this would, of course, represent the code. This would just be 15 independent codes. So you can think of large code, but that wouldn't be very interesting. So what we're going to do is now, spatial, you can kind of see already, right? There's a spatial structure to it. And the structure right now is one of a circle. But what we now still need is the coupling. And so what we do with the coupling, well, we simply take edges here. And what we're going to do is we're going to start connecting them. And so there are many ways to do it. And so I'll just show you two different ways of doing it. Imagine the following in your mind right now. Imagine that for every edge that you have in here, you maybe flip a coin that has 3 sides. And the coin might say left, middle, or right. If the coin comes up with left, what you're going to do is exactly you do what you did here. Okay, instead of connecting over here, you're going to connect to something on the left. If the coin says middle, the edge will stay. If the coin says right, you will connect to something on the right. Okay, so you just do this whole thing will look like a picket fence. So if we do this for all of them, it might look something like this. Now, here's what's important. You don't just randomly flip things and randomly connect them. Okay, you do it in such a way that the local connectivity of these nodes stays preserved. So meaning whatever you do, and whatever you had beforehand, if you beforehand had a 3.6 code, that every node had degree 3 and every node had degree 6, you do it in such a way that after you do the flipping, again, every node has degree 3 and every node has degree 6. So locally, you cannot tell that you're now in this coupled thing. Locally, if you just look at the degrees, they have exactly the same structure as before. Okay? But now they have in addition this connectivity. Make sense? So if we do that, okay, we don't know yet why. Then if we do this, then of course this stays completely, this is circular symmetric, right? There's complete symmetry in this picture. Now, if we did that and we use now message passing on a code like this, we would see exactly the same behavior as for the underlying graph. Okay, everything I told you before is true for this graph. Nothing interesting happens. So in order for something interesting to happen, we need to break the symmetry. And in order to break the symmetry, we somehow need to break this chain. We somehow need to break this this whole circle. And then one way we can do it is the following. Unfortunately, again, this is you don't see it here. So
this procedure, I think that it reminds of my colleagues students way
of the protographing.
Yes.
So it's yeah.
Yes.
It's maybe somewhat connected, except you see if you thought about this the graph cover, okay, then what would happen is that you would take like edges. So this edge would be an equivalent here, and you would all do this. You don't do this here, okay? If you did that here, what would happen is that this edge could connect to any of these things in here, okay? But this edge only can connect to its neighbor. So it's like a photograph in which you can only connect neighboring sheets of paper, okay? And so so there's a slight difference, and that's crucial. Yes.
So earlier you were doing it only for the blue notes and not the red notes.
No, it's the same. It's just that it doesn't matter because you can, you can anchor one and then think of this, or there are many ways of doing it. I'll show you. Okay, the exact way of doing it. So now we need to cut it. Okay, so how do we cut it? One way to cut it is, and I apologize again, you can't see it, is the following. Simply take one set here, let's say the set of variable nodes you have, and simply set them to a known value. Okay, if you all set them, for example, to 0, and you agree beforehand that there will be 0, and you agree at the decoder and the receiver that there will be 0, and set forever, then what will happen? You take some degrees of freedom away. You can no longer set these values to whatever you want. Okay, so they're set to 0. But what happens is now the following. If this value is permanently set to 0, then this value, when let's assume it connects over here, it will simply, it's 0, right? It's fixed value 0. And so this is the same as not being here. Okay, so setting something to a fixed value 0 is the same as simply cutting the edges up here and having our structure that we have. Okay, so it's the same structure, except that we basically cut with a knife out one section here. And if we do this, then it's slightly nicer to think of it in a line, okay, no longer on a circle, although that's just for aesthetic reasons, okay? And that's our spatially coupled code. So now, what are the parameters that we have here now? Well, we have, so what I told you is that I connect to neighbors, so there's a connection with, right now we're just thinking of connecting to nearest neighbors, but for the analysis, you might take a window and connect it within this window, okay? But not much is lost if you're just thinking of connecting to the nearest neighbors on the left or right, but in general, there's a window. We have the length of the chain, so we're having how many copies we started with, basically, right? And then we're having basically the size. So this is one, so each of those things is one, so if you think of one of these things here, that's one traditional graph that I had beforehand. So each of them has a certain length. We're taking L copies of this, and we connect them via neighbors up to size W, right? So these are the parameters. And then I still have the parameters of the basic code itself. So for example, this is every variable node is degree 3, every check node is degree 6. Okay, so now let me just show you another way of doing the same thing. It's just a different picture. So now I show you the same picture, but with a protograph thing. Perhaps that makes it, it makes it more confusing than just close your eyes for a minute. If it makes it less confusing, then maybe just check. Depends on if you like this representation. So this is the same representation. So each of them is now a protograph. So each of them represents one of these codes that I had beforehand. Okay. And now, if you have this representation, it's very natural, for example, to think of the following, to think of a regular way of doing it, right? So now, this is the following. This is now the protograph for the spatially coupled one, right? So again, you see that every variable node has still degree 3, every check node has still degree 6. But now, what happens is that every check node, for example, has exactly one connection down here, one to the right, one, let's say, to the right. Okay? So this is a much more regular way of doing it. So there are basically two ways of doing it. Either you can do it randomly, or you can do it in this regular way. For proofs, random is the good thing to do. That makes it easy. For practice, actually, these photographs work much better. Okay? So this is what you actually would do. The other one is what works well if you want to prove proofs. So in terms of the thresholds, they're the same, but if you look at other parameters, for example, rate loss, number of iterations, they can be different, okay? The thresholds are the same, but they're not, I mean, they do differ, so it does make a difference.
The protographs you start with are identical in practice?
You could, so right now, actually, in all this construction, irregularity will not play a role. You could add it, but kind of there's diminishing interest because you don't need it. But there might be a reason, right now we don't know why you would add it, because without it, it works already. But but you could do it. There's no reason not to do it. It's just that we don't see right now why it's needed. Okay, and that's why it's not done. But you could do it. Okay, so so what happens here? So yeah, so there's now. So this is the construction. So that's maybe just something, because I'll come back later. I apologize again that it's very hard to see this thing. So when you do this structure, what you will see is that there will be some checks here, right, that should have some connections outside here. And then there are some variable nodes here that should have some connections here, right? So in the interior, everything works, but since you cut the chain, there's something that happens here, right? So how do you do that? Well, what you do is, the idea is that you kind of help the code. So you make the boundary condition most favorable for decoding. And what does this mean? Check nodes are not good to have high degree. Okay, the lower a check node has, the more reliable it is. So in order to make that, you simply assume that these things are again fixed to 0. Okay, so they're not there. And at barrel nodes, they like to have high degrees, so you actually add on the left these check nodes. Okay, so the final graph is exactly this graph that you have here. So that's the graph that you would have. And so what do you see? As I said, they still have the same structure. They have this extra spatial structure, but there's one extra thing, and you pay a price. As you can see, there are 2 more check nodes that you have. Okay, locally you have for every check node 2 variables, but here you have 2 extra check nodes that you have, right? A check node, every check node takes away 1 degree of freedom, right? It's 1 extra constraint. So this means, compared to the original code, this structure has slightly lower rate, right? Because you lose a little bit some rate in the boundary. Okay, and we'll get back to it a little bit. So there's some price.
So since in practice, if you do it this way, it looks like it would be something like a block diagonal matrix or something like that.
Yes.
Is that
so for example, if you do the same construction in compressive sensing, it turns out it's basically a diagonal, a band matrix, which has some special structure at one end. Okay, that's the equivalent.
and it's hard to analyze, but it's hard to analyze the structure analytically.
No, we'll do it. Okay. Well, can be done with, I'm not going to show you the whole program, but okay. Good, okay. So now, as I said, there are many constructions, protograph construction, random construction. What you really want to do is for good performance is the protograph. What you want to do for proofs is the random construction, because you just have fewer degrees of freedom to deal with. I guess it could be done for the protograph too, but it's just more complicated. Okay, so now we get to, thanks to David, we get exactly to this question. Okay. And we're going to ask, why on earth might you want to do such a thing? Okay. And so let's follow exactly David's capacity approaching scheme. Okay. And simply increase the degrees. Okay, and see what happens. So what we do is you have the degree dl, and then let's stick with a rate 1/2. So if the rate actually turns out, I didn't mention this before, but the rate is exactly 1 minus the variable node degree divided by the check node degree. So if you keep the check node degree exactly twice the variable node degree, then you will get a rate 1/2. Okay, so we are now back to the uncoupled case. But what we do is we do exactly what David suggested. We simply increase the degrees and we check what happens. Okay, and again, this is just for the BC, but you could do this for the general case. So this was the picture we had for the 3.6, right? 43%, right? So now what happens if I'm increasing and I'm going for the 4.8 instead of the 3.6? Has exactly the same rate, it's just the degrees become larger, right? Now, one slight disadvantage for going 4.8 is that you have slightly more computational complexity because now you have nodes of higher degree. But if it performed better, that would be perfectly acceptable. Okay, so let's check what happens. Well, unfortunately, the curve moves to the left. Okay, so this means that now its threshold is only about 38%, right? And remember, capacity is about, the threshold for sharing capacity is about 0.5. Okay, what happens if you do this 510? Okay, and unfortunately, this goes down monotonically. And it's not very hard to show that if you let the degree go to infinity, that the threshold will converge to 0. And this is for the BC, but if you look for general case, then for any channel, you can give a threshold. So that's the threshold, that's the equivalent. So H is the entropy, that's the equivalent of the epsilon. And so you would like this threshold. So this is in general an upper bound in the threshold for generic channels. And you would like that to be 1/2, but unfortunately what you can see is the following. Forget about this bottom part here. The bottom part will basically just be 1 for high degrees. So what does this depend on? It depends on dr, so the right degree. This thing here will quickly go to 1, so you can forget about it. So this is the binary entropy function of 1 over basically the square root of the degree. Okay, so in general, if the degree becomes large, then this point, okay, whatever, the largest entropy that the channel can have, 1 minus the capacity, unfortunately that goes to 0. Okay, and it goes to 0 at least that fast. That's just an upper bound. So unfortunately, you're sunk. Okay, you cannot, if you just do higher degrees, under BP decoding, this is not a good code. Okay, we'll see in a second that if you could do the map decoding, the code itself would be very good, but the decoder unfortunately doesn't work.
Check nodes with all of them to all of them.
So why doesn't it work? So the problem is that decoding on this graph is a dynamic process. And so you need basically the right dynamics. You need that in the beginning, you get some information. You need that some of the nodes will be able to decode. And then these nodes will have other nodes. And then these nodes will have, again, other nodes. And you need that basically there's a steady trickle of always just enough information to carry this process forward. If you take very large degrees, what happens is at the check node side, if they're very high, basically, if you have already not very reliable information that goes now to a degree 100 check node, the information gets so much deteriorated that basically there's no information flowing back to the variable nodes, and the process never gets started. Okay?
So following this logic, it seems that you force the better than 3 things.
Okay, so that's, David, I couldn't have hired you. Okay, you're giving me exactly the
Worry, I'll give it there at the end.
Huh?
There'll be a bill at the end of the lecture.
Okay, good. I hope I can afford it. So let's check, right? So what should be? So let's assume that one suggestion is that we simply take the two full code, right? And let's try to figure out what the epsilon BP, so the threshold for the 2-4 code is. Okay. So now, how do we figure this out? Remember, okay, sorry. So my claim is that for the 2-4 code, what we'll get is a threshold that is exactly 1/3. Okay, but let's quickly just go through which is actually worse, right, than the 0.42. So how can we do it? So remember, right? So this function f of epsilon x is the following: is epsilon of 1 minus x. And so what do we have here? Here's the check node degree minus 1, so this is 3. And then here we have the variable node degree minus 1, which is 2 minus 1 is 1. Okay, so that's the function. And so what do we have, right? We start with x0 is epsilon. And then we have in x of L plus 1 is equal to f of epsilon x of L here, right? So we're looking at that and we're trying to see the largest epsilon for which this converges, right? And another way of saying this is that there always has to be progress. So if I'm looking at x minus f of epsilon of x, so if I'm looking what the value was beforehand and what the value will be after one iteration, right? Hopefully this value is always smaller, right? If this value is always smaller, so the condition is that that thing here should be, let me do it maybe the other way around. Let me do it like this, okay? So this value is always larger than this one. So if that's equal to 0, where 0 smaller than x smaller than epsilon, if that's true for a particular epsilon, right? Then this means that this recursion will go to 0. Does everyone agree? Right? So this is a particular value that I have at some point in time. This is the value that I will have after one extra iteration. If this value is smaller, it means it makes progress, right? So if this is smaller, then this minus this will be negative, right? So if this is negative everywhere, right, then I hope you agree that this recursion will go down, right? So that's certainly a sufficient condition. It turns out it's also necessary, right? You might think at first that maybe it's not necessary because maybe it can jump over something, okay? But this is equivalent. So this going down, x of L going down to 0, or limit L going to infinity, this condition, okay, that this and this condition is equivalent, and it turns out that even you can even look here at 1 that's also equivalent. All of these are equivalent conditions. Fine? Okay? So now we just need to look what this function looks like. So let's just see what the f of x looks like. So now, since I told you already that I think the threshold is a third, let's maybe just try to see what it looks like for a third. And if you plot this function, I think this function will look like this. So here the function has slope 1. Okay, so this is just calculus. Okay, so this function here has slope 1, and this function here is exactly this thing here is a third. Okay, so if you just have to plot this out, it's not hard to see. So what I'm claiming is that f of epsilon x is increasing and concave. Just take the derivative and plug in x's. Okay, sorry, I'm plugging x being 0 anymore. We'll see it's increasing from a. It takes on the value 0 at 0. It takes on the value epsilon at 1. Okay, so the function looks like this. So now take this minus the x, right? This is exactly the function x here. Okay, so what you will see is that the function looks like this. It will be, well, I don't know. It will look like something like this. It will be negative everywhere, right? Because this is just the x here, and you take the difference, and it's just exactly this difference that you see here. And you will see that this goes exactly to, so as you start here, this will be negative everywhere, and exactly at 0, it will just become critical at the third. Okay, and if you go just a little bit above the third, it will become positive here. Okay, we'll have a little bit something here, and if it's slightly less, then the slope here will be. Okay, so it's exactly a third is differential. Fine. Okay, so now why is that useful?
And that's actually true even for map decoding, right? Like not if you
so it turns out that even on the map decoding, the threshold for this code, but that is a little bit more complicated, it would also be a third, and that has to do with the fact that it's exactly here, the critical point is exactly here, and that's what's called the stability condition, and even the map decoder could not do better. Okay, but that's a different story.
You gave a calculus explanation.
Yes.
But you give an intuitive explanation.
So the intuitive is the following. If you look at the bipartite graph, okay, and you do the following, you pick exactly an erasure property epsilon, then the following will happen. If you are with epsilon that's larger than a third, okay, then if you look at just the graph that's remaining, so you erase all the edges that emanate from points that are known, but you leave all the ones in that are edges that are not known. Okay, so I mean you have your original graph, right, the bipartite graph, and now you look at the induced graph that's induced by all the variable nodes that have been erased. Right? Look at this bipartite graph. If epsilon is less than a third, okay, then this doesn't have a connected component. So there are no cycles and no connected components in there. But if epsilon is larger than a half, then you get a giant connected component in there. In particular, you will get cycles in there, and every cycle corresponds to a covert. Okay, so this is exactly the same phenomena that you get for random graphs, where the threshold, the threshold function that you have in Erdős-Rényi graphs, where you suddenly get a large connected component. And here, having a large connected component means that you cannot, okay, because there are code words in there, and you cannot distinguish between these points being set 1, 1, 1. So any cycle that you have in there, which now for sure you find, you can set it either to 1, 1, 1 or to 0, 0, 0. Okay, and both of them are valid. Okay, so that's the intuitive.
So we're discussing this point about the effect of increasing the degree. Starting with 3, 6. So now we're going to start from 2, 4.
Right.
You're saying that the two phenomena going on in 6. 2, 4 is too sparse in some sense, so that you don't get a giant component.
So it's not true that in general that every time you increase the degree it gets worse. Okay, this is just for the rate and a half. I can give you other rates where it might get. So this is not a general thing. Okay, so it's true. It's always true that if the degrees go up, this thing that I gave you, that it always will go to 0. But it's not true that it's a monotone function starting right away. Right. So let's assume maybe I give you a rate a quarter. I don't know the numbers. It might very well be that whatever a 2, if you do whatever 2, 8, and then 3, 12, and so on. That first it's increasing for a few times and then decreasing. Okay, so it's not as simple as just saying it's always increasing.
Is it always unimodal? So you increase?
Maybe for regular ones, right? But not even that. I'm 100% sure. Okay, it's.
Just for example, we bring 2, 4, 3. Let's just forget about integers and let's do real numbers. Let's ask x and 2x. Let's maximize the x and y.
For this one.
Yes.
Yeah.
Will you get to half? Will that maximum value be? Am I approximating a non-integer value by doing this?
Yes, I'm pretty sure no. Okay, and I can tell you a little bit why no, but maybe now is not the perfect time. It has to do with this curve. Okay, in order to get to a half, this curve basically would have to be a square, and And these curves, you can see they're always these C-shaped curves, and they will continuously change, but they will never become a square. And as long as it's not a square, you cannot get capacity. Yes.
So then related to that, so as you increase your degree and then twice the degree, as you increase this degree on the left, twice the degree on the right, then for the variable nodes, it gets better as the degree.
Yes.
But for the heritage,
Right. Right.
So therefore
There's a competition.
And so based on that, maybe somewhere between what Chandra said, there will be somewhere between 2 and 3 on the left.
There might be an optimum, okay?
Right.
Now, it's not clear what a fractional degree would mean, but there will be an optimum. But it doesn't mean that, I think I'm pretty sure it's not true in general that even unimodal, I think in general would not be true. Okay. I don't think so. I don't see necessarily a reason that.
But so let's say that because of something like the function, you increase it, you make vector on the left and works on the right, and then somewhere in between, let's say that you wanted to get one, maybe this would lead you to something like spatially coupled, because you can do some degree like let's say degree 2 and then degree 4, and then you switch to another degree, and then when you unravel them, you kind of imitate.
So okay, the role that the degrees play is equivalent to the role that space plays for spatially coupled. The difference is that if you do degrees, the degrees depend on the channel. The spatially coupled has the property that it universally adapts itself to the channel. Okay, so they play the same role. That they play the role of the dynamics, how the dynamics is, but they behave in slightly different ways.
Unrelated question. You are in a spatially coupled code to set some variable nodes to fix their values. You could have done the same thing with just like a single graph. Maybe you will not be able to do the analysis like you're able to do it, but then you might be able to simulate and see.
So the idea that maybe a standard graph could have hidden inside kind of a structure like this, it could be a structure. I'll tell you.
Maybe even doesn't have the structure, but maybe you set some variable nodes to
right. But what's crucial here is, it's exactly the dynamic process. So you can, if you just randomly set things, it's just like a code with a different degree distribution. You might have as well started with it. So it has to be a very specific thing that starts this nucleation process, and this has to grow. So there has to be a very specific dynamic. So it could happen, for example, that in the standard graph, you could conjecture that if you pick a standard graph, that you could label the nodes in such a way that they basically correspond to these things that you have. Okay, I don't think it's true, but we don't know. Okay, so I think it would be too much to ask. Right? So if you knew that, and then you would set the very specific things to 0, something similar might happen. Okay. Good. Okay. So now, why was it useful to go through the exercise for this 2-4? Okay, because now let's just see what happens for spatially coupled. Okay. So why might spatially coupled codes be good? So we have just seen that if I take a code and I simply increase the degrees, then eventually the degree will go to, eventually the threshold will go to 0. So now let's do exactly the same thing for spatially coupled, but just to make it a little bit easy. So this again is spatially coupled structure. The only thing that's different now is the following. These edges are bold. Okay. What I mean with the bold edges, these are actually 2 edges. I was just too lazy to draw 2 edges. I drew them bold. Okay. So this node actually has degree 4, not degree 2. Okay. It's just each of them, think of them as two edges. Okay, this doesn't, just if that confuses you, this doesn't mean they go to the same check, right? Remember, that's a protograph. It just means a check on this side goes to a variable node on this side, but it's not the same variable node that the edges go to, right? It just goes to some node, but behind this node there might be 1,000 other nodes that hide, and so it means one edge maybe goes to node 374, and another node might go to the node 1. Is that clear? So these are not really double edges as before. Okay, might be a little bit confusing. So let's do this. Okay, so let's do exactly the same game now. So this is now something, this is the equivalent. So what is this now? Okay, so here we see that we have degree, well, this looks like degree 3, but these are all double edges. So this is a 6, and this is 12. Okay, so this is a 6-12 code right now already. And so now what happens? Well, the following happens. So this is a 6-12 regular coupled ensemble, and it's just slightly easier to explain it with these double edges. So now the following. Let's assume I have again the BEC, okay? And let's assume now that what I do is that I simply ignore during the decoding the rest of the graph. Okay, when I decode the first instance here, I simply ignore everything have to the right. And that I can do because that makes the code only worse. I'm simply ignoring some of the constraint and some information that I get from the code from the right. When I do message passing, any edge I have can only give me information, okay? Can never harm, right? And so if I simply take them away, it simply makes it worse. Does it kind of make sense? So if you look at that back, okay, so what could happen is in general that this edge might carry information and tell me what this value here is. If I take this edge away, right, if I ignore whatever happens there, then I'm simply ignoring part of my information during the decoding process. So now let's look what happens, right? So I take it away, but what is this thing, right? This thing here is a 2-4 code, right? Because remember, this is double edge, this is double edge. This is degree 2, this is degree 4, right? So we just computed that this has a threshold of a third, right? Okay, so this means if the epsilon is less than a third, I can for sure decode this thing, right? But once I decode this, okay, then now look at the rest. If I look at the rest, unfortunately, again, I apologize that this it doesn't show. You can maybe, this is the extra thing here, okay? So this we already decoded, okay? So once we decoded this extra section here, there's simply some information. This information flows in here, but these are just constants. It's just a constant shift, and what I've left with looks exactly the same what I had beforehand, just with the first section already decoded. Clear? So what I can always do is, rather than thinking of the spatial coupled structure, I just decode the first section, ignoring everything. Once I've decoded it, I erase it, I decode the second section. Okay, so if I do this, what is the threshold of this code? Well, the threshold of this code is at least 1/3, right? Because I've shown you that it will work for 1/3. Make sense? But now what is, if I do, for example, instead of 612, let's assume I did an 816 code, right? Exactly the same structure. I'm just increasing, I do exactly the same experiment that you had before, and again, rate it half. But you can do the same thing, right? You can, again, ignore everything here, and you see these two guys here. Again, this will decode up to array the third, up to epsilon the third. Now, this is gone, and it's done. So it doesn't matter what the degrees internally are, right? So this structure, even if I go to 1,000,000 and 2,000,000 degrees, it will have threshold of at least a third. Make sense? So, that's not what we want. The threshold should be a half. I hope we get to a half, right? But you can see that this behaves in a very different manner from the previous one, just by this trivial argument, right? For the previous one, with a trivial bound that says it goes to 0, like entropy of 1 over the degree, 1 of the square root of the degree. This one says that the threshold, no matter what the degree is, at least 1/3. Right? Okay, so now, how do we analyze this now, right? First, maybe the question: what time is it right now? Should we take a break? Okay, so we take a break, and when we come back, we'll see.